time we wrote a really silly, hello world type program. And so what I'd like to do is basically just rewrite that. But then I want to talk about how basic programs are actually stored in memory, because this is not what you would think it is. All right, so let me just type a simple, oops, would help if I'm in the right. Okay, so there's my program. And you'll notice that when I typed it, I put a space between um, print and hello, but then when the list came back out, it removed that. So that space is not necessary, and therefore we don't need to store it, but it certainly does make it a little bit more readable. Okay, and so there are plenty of places where spaces get ignored, even though it might be nice if they didn't. Okay, so wonderful. So what I'd like to do then is I'm going to um, look at a location in memory. Okay, so I'm going to print peeking at location. Sorry, let me do the arithmetic again. 8 times 2049. Oops. Okay. And if I do that, I get 22 or 22. Okay. Now remember, everything in BASIC is in decimal, not in hexadecimal. Okay. And so how do we interpret what is there in memory at that location? Okay. And then I could continue and I could do the same thing and do 2050. So let's do it. Okay, so would somebody write down, huh? Yeah, so 2050 is, and in fact, let me just sketch this, make like a little micro table up on the board here of these values. Okay, so the 2049, okay, so the memory address is in hex, in decimal, and then let's say value in decimal and value in hex. Okay, so the memory address that I'm looking at in hex is 801. Okay, so how do I convert that to decimal, right? Well, where is the 8 in the, which position is it in? Looks like it's in the hundreds place, but in hex, what is that? The 256's place, right? Because what's the power that you go up by each time in hex? 16, right? So I have the ones place, the 16's place, the 256's place, and so on, right? Okay, so 256 times 8 is 2048, plus 1 is 2049. Okay, now what's so special about the number 80801? That's actually the memory address where a basic program is loaded in. That's the beginning of it. Okay, and so what is that in decimal? What did we say? 2049. Okay, what did we see in that memory address? We saw decimal 22, which would be what in hex? 16 or 16, right? Because what's 22 divided by 16? 1 with how much left over? 6, so there we go. Okay, does that make sense? All right, so if I continue this, and Michael, I'll let you be the chalkboard guy. So let's just keep going a couple of memory addresses further, okay? And in address 802 is, right, is 82 decimal, and we'll convert these to hex later. Okay, let's continue. And obviously the best way to do this would be to write a loop, but we'll just go 10. Zero. Okay. 153. And somehow I feel like I had the wrong address here. Hang on one quick second. Um, um, oh, no, that's the right address. Okay. Um, okay. And then let's keep going a little bit more. So 2054 is 343. That's way too big. That doesn't make sense. That's too big. Yeah, it shouldn't be that big because it should be a number that's less than. Um, this should be a number underneath 256. Let me check it again. Oops. Oh, I bet you it just. Yeah, it. Okay, yeah, it's 34. So, oh, I know what it was. Okay, so here's what happened: is this three was already there on the screen, and it just didn't overwrite that with a blank. Okay, so 34, not uh, uh, 334. Okay, so 2055, we get also 34. No, sorry, 72. God, I must, yeah. This is why you shouldn't eat pizza for lunch, guys. 69, of course, we had to get that. Um, yep, 76. Okay. And then let's see. Also 76. Then 79. Okay, and I think at this point you guys will get the idea. Okay, so we've got all those values, and what I want to do then is look at, okay, what are these in hexadecimal, okay, and then also organize them. So for the sake of doing this, let me open up a quick Excel file, and let's basically type those values in just for to make this a little easier to see, okay? All right, so let me do in hex decimal, and I'll blow this up so it's easier to read. Um, so let me zoom in so it's nice and big. Okay, so here we have 801, 802, 803, 804, 805, 806. How many lines did we go down? Yeah, okay. Well, we'll do that. And so this was what, 2049, 2050, 2051, 2052, 2053, 2054, 2055, 2056. Did we go any further than that? Yeah, we kept going. Okay, so we went 2057, 2058, 2059, 2060, and so on. Okay, and then we would have 809, 80A, 80B, 80C, and so on. Okay. All right. What were the values that we got in decimal here? So we had, what was it, 22, 22, 8. Was it 82? Really? Okay, that surprises me. Let me go back to here and just double check. So print peak of, what was it, 2050? No, it's just 8. Okay, sorry. So it's that same overwriting thing. Okay, so 2, 2, and 8, and that's correct. I'm going to type it as 08 here. So let me change all of these cells from number to text so that it doesn't lop off zeros. Okay, got that. All right, so this is 08. And then 08 in hex is 08. What's 22 in hex? We said it was 16. Okay, what was 2051's entry? 10 in decimal, which in hex would be what? Okay. Yeah, 0C. No, 0A. Right? Because 10 is A, right? Yeah. Okay, what's the next one? 0. Okay, so that's obviously 0. All right, 2053 was what? 153, was it? Okay, and in hexadecimal, that is 99. I'm looking at I've got a quick reference table here. And we could continue with this. So then what's after 153 was followed by 34? Okay, in hex, what is 34? It'd be 2, 2, right? Okay, what was next? 7, 2, which is in hex, what's that? 4, 4 is, so it'd be 4, and then 8. Okay. All right. So all I'm doing, right, is converting these things into hex, right? No big deal on that part. So let's keep going. All right. What was it next? 6, 9, and then 7, 6, 7, 6, 7, 6, and then 7, 9. And did I never poked 26 or peaked 2060, did I? Okay, that's okay. You guys will get the idea here in a second. All right, so what is, let me just open up a quick Python console to do the conversions for me. So what was it? 7, 6, 9 is 4, 5. Okay, and 7, 6 is, or 76 is 4C. And those are the same, okay? And then 7, 9 is 4F. Okay. You guys notice anything that looks familiar or perhaps ought to look familiar? Well, what's our first line of our program anyway? Printing. What are we printing? The string. What's inside that string? Hello world, right? All right. So does the sequence 4845 4C 4C 4F ring a bell? That's ASCII for hello, right? So let's pull up an ASCII table and double check that. All right, so what I'm going to do is I'm going to put the ASCII table on the right and the Excel spreadsheet on the left. And would you look at that? Okay. What was the first letter? The 48, is that the capital H? It is. Right? Okay, does that make sense that we ought to be seeing that if we're looking at where our program is being stored in memory? When that's part of the program, I would expect so, okay? But what about 2-2? What's that? Yeah, that's the quotation marks, okay? And then we've got some other stuff here that's not quite so clear. Okay. Um, but let's think about what was the very beginning of our program, the first line of it. What did it have? No, we didn't have a money sign. A 10, right? What was 10? What role was that playing in our code? That was the line number, right? And so 0A, of course, so what was in memory is 10, followed by a 0. Okay, it's not a space. It's line numbers don't. Okay, so fair question. How many? Well, okay, if we use 1 byte to encode the line number, what's the maximum line number that we could have in a program? 255, right? Because 0 could be a valid number. Okay, do you imagine that 256 lines of code is probably not sufficient? Yeah, okay. So line numbers are stored actually as 2 bytes rather than 1. Okay, what this means is what's the maximum line number that you could have then? A lot bigger, basically 65,536. Now, in practice, are you ever going to have that big of that many lines? Okay, is that possible to have that many lines in BASIC on this computer? Bingo. If you had enough RAM, but how much RAM do we have? We only have 64K, right? So the maximum number of, like, we literally have 65,536 memory addresses. And a line of BASIC takes up way more than one line, or I mean, one memory address, right? So the maximum line number you can have is 65,535. But in practice, you would not have that many line numbers. Of course, this is one reason. What have we done with our line numbers? Yeah, we skipped them, right? So, like, if I can go all the way up to 65,000 line numbers, but I'm counting by tens or hundreds or something, then I'm not going to run out of memory. Okay, so 256 lines is not sufficient. I mean, for a stupid Hello World program, that's not bad, right? But for an actual program that's going to do something interesting or like a game or something, that's obviously not sufficient. Okay, so that's why the 0 is there, is because we've allocated that our line number could require 2 bytes of memory to store. Okay, so this is a low byte and high byte of the line number. Okay, and then we're going to fill in what's next, or what these other addresses are. Okay, so I would like to actually fill in more of this table. Okay, so let me continue here. I'm actually going to change these to numbers, this column, so that I can have it do automatic computations for me, just because I'm lazy. Okay, so let me change this set of things to numbers. And then what I can do, oh, and I don't want freaking decimals, stupid Excel. Okay. Because then I can be lazy and say, do the previous value plus 1. Oops. Okay, so I'd like you guys, and you typed in your Hello World program advice just like I did, right? Okay, peek for me, and so let's do it this way. Alex, do 2060, 2061, 62, 63, 64, 65, 6, 7, 8, 9, 10, so 2070, 2071, and Michael do 2072. Okay? And this way, this will just parallelize this, and so we can Oh, sure. It was the command. You would do print, peak, and then your number. The same way? Okay, well then redo it as just print hello world 20 go to 10. Okay, because obviously if we have the wrong, if you guys are looking at memory where your program is different, then your values aren't going to match mine, right? Oh, and there's a function to convert it to hexadecimal. Hallelujah. Okay. Well, what would you be expecting to see in box number 2060 or the comma, right? Okay. And so what did we get? Who did 2060? Alex? Oh, I'm sorry. Okay. Well, 2060, I'll just cheat. It should be the comma, right? Which is, where's the comma? 54? Oh, sorry, that's octal. So 4 decimal. Okay. So this is the comma. And then you did 2061. What did you get? Uh, am I off by one, guys? Oh, sorry. Let me go back to Vice. Um, all right. So print peak 2060, 44. All right, and let's do 2061, 160. Okay. Well, okay, I'll just go through this. So, all right, so 2062, what do we have? 87. Okay. 2063. Yep. Okay. And of course, this is O or capital O. What's this one? W. Okay, so we should expect to see this following. Okay, do the numbers jive? You sure? Because I said so. Okay. Yeah. No. Fair question. Right. Um, so I know that basic MIP programs are always stored starting in that memory address, and that's why we're looking there. Now, who decided that that was the location basic programs would be loaded into? The people who designed this computer, right? Did it have to go there? No, it could have gone someplace else, but that's just what they picked. It also bothers me that they started with 801 and not 800, but 2061. Okay, now that's actually a good question. So, what are we expecting to see there? The space, okay? But what is the space in ASCII? It's the space is here, decimal 32, hexadecimal 20. Okay, what did we get? You get 32? Really? Okay. No, there's actually a reason for these two different numbers. No, you totally got 32. Okay. I think this might actually be a version issue on the emulator. Okay, because, all right, so let me just write down here next to it. Michael got 32, which is 20. hex, which is a space. Okay, now 160 or A0. Let's look at our ASCII table. Where is 160 on here? It's this weird symbol, okay? But we're looking at the wrong table. What we need to be looking at is not the ASCII table, but the PETSCII table, because that's what the Commodore was actually using, okay? Now, the difference between it and ASCII is not huge. The letters are all in the same places, okay? So for example, where was our hello? Our H, 72 or 48 hex, right? Everything's cool? All right, so let's look down and find where is 160 on this table, okay? Yeah, it's up one here, okay? It looks like it's this symbol. Okay, so this is interesting. There must be a bug on mine because I looked this up before, and ASCII is called a non-breaking space, okay? And essentially it's a space that can't get line broken. And I'm not sure why the emulator is doing it. This may actually be a Mac versus a PC thing. Does anybody, who else, Artie, did you get 160? Or did, for 2061? Or did you get 32? Okay. Well, then I don't know what's up with my computer, so I'll figure it out. Okay. It should be 32. Okay. So I'll figure out what's up with that. But oops, the wrong thing. This should be 32, which is the space. Okay. Okay. Now let's keep going. What did 2064? Who did that one? What'd you get? 82, which is 52. Is that the R on our table? 52. Or sorry, these are in. We want the PETSCII table or ASCII table. 52 is R. Okay, good. All right, next, 2065. Who had that? Okay. What'd you get? 76? Oops, 76, which is 4C hex. Is that the L? Yep, looks good. All right. 2066, who had that one? 68 or 68, which is 44. That's the D. Good. Next. Who had 2067? And what? Okay, let me see, because you might be typing something wrong. $33. I don't know what you did.
I feel like I just typed the same thing you did.
Yeah, well. Okay, so what'd you get? 33. Okay. And which is 2-1 hex. What does that correspond to? Is that the exclamation mark? Okay, good. And then 2068. This is where it's going to start to get interesting. Who had that one? Patrick? 30. You had 33? Oh, we should have the closed quote. So what's 20 for 68? Okay, which is, that should be the closed quote. Okay, good. And then what? 2069? 34? Okay. You guys must be off by one. Yeah, and I bet you it's that space. Okay, so let me just do it so that we're all consistent here. Peak, all right, so we need 2069, 0. Okay. And then 2070, 30. okay? And then let me just keep going a little bit further. Okay, and let me do dec2 hex of this. Oops. And then I'll change it to a text cell, or I'll change these to number cells. Okay, so I got 2071, I haven't done that one. 8, that's what I was expecting. Okay, so 8. And then 2072, what do we get? 20. Okay. And 2073, what do we get? Should be 0. Yep. Okay, and then 2074. Here, let me clear these. 137. Okay, and then 2075. 49. Okay. 2076. Oh, I lost a parenthesis. Yeah, sorry. 48. Okay. And I need to keep going a little further. Okay, and then let's see what's next. 2077. Good game, by the way. 0. That's what I'm expecting. Okay, and then 2078. Oops, I lost a parenthesis again. Also a 0. And we will automate this process later, I promise, because obviously this is a little bit tedious. Okay, double zeros. Okay, so so what we have is how did I label it here? Yeah, okay, so that, okay. And then some of this other stuff is not going to be particularly clear, okay? But what is 3.1 hex? On our ASCII table? It's the digit for a 1, right? So this is 1, this is 0, and then we have 3 nulls. Okay, so we got a few other things to figure out still, because there's some of these that if you look at their corresponding values on the ASCII table, they're not going to, you're going to look at them and say, oh, that's some weird character, but that's not quite right, okay? So there's also things in here that don't seem to correspond at all to ASCII. So for example, this 8 that's right here, right? What's ASCII number 8? Backspace. That doesn't make sense. Okay, so it's not actually backspace. What it is actually a pointer. Okay, so what I want you to look at is, let's go up to the very top, okay? And we had here, our program started with 2208. Where is 0822? Was it 22? Let me double check that I typed it right. Sorry. What was it, 2049? Yeah, it was 22. Okay. Oh yeah, sorry, I'm being stupid. Okay. All right. So 22 is in decimal, right? What was it in hex? 16. Okay. So the way I want you to look at this 816 is think of it as 0816. Okay, where I'm specifying the low byte and then the high byte of a memory address. Is that okay? Okay, I'm going to explain why it's 0816 in a moment. Okay, but can you just run with me? Let's take that as it's just like with the line number, I'm giving you the low byte and the high byte. Okay? Okay, so just accept that for a moment. What is in memory address 0816? Whatever this thing corresponds to, okay? But whatever this thing corresponds to, where in the program are we when we're getting down to this point? The second line, okay? So what that value is, 0816, is a pointer to where the second line of code begins in memory. Okay, does that make sense? Why do we need a pointer? Okay, so the way that this is stored is that the very first thing for any line that you store is the pointer to the next line, then the line number, then the actual contents of the line, and then all lines are null terminated. Well, the interpreter, it's not a compiler, right? And let's be clear, what is the difference between a compiler and an interpreter? What does a compiler do when you give it code? What does it spit out? It spits out machine code. The interpreter is not spitting out a machine code file. It's basically generating machine code on the fly and running it. Okay, so there's a difference. Okay, okay, so that very first thing is actually a pointer. Yeah, Evan, question. Yeah? Say that again? Yes. Okay. So what we have here is this is the high byte of pointer to next line. This is low byte pointer to next line. Then down here we have low byte pointer to next line, high byte pointer to next line. Okay? All right, now, what you guys might be irritated with is, what was this one pointing to? It's pointing to right here. Is there a third line in our program? No. Okay, so every line of BASIC, when it's stored in memory, each individual line is null terminated. Okay, so for example, where does the first line end? It ends after the quote from Hello World. And how do I know that I've hit the end of a line? Null terminator. Okay, and then the next line begins with pointer to the line after that, line number of the line I'm on, and contents of that line. Okay, is that okay? So this null terminator at 2077 is terminating the second line. And then a basic program is double null terminated at the end of it. So if you look at any basic program in memory, you'll see at the very end of it 3 zeros in a row. What's the first of those zeros? the end of the last line, and then the double no terminator at the end is telling you that you've hit the end of the program. Okay, does that make sense? Okay, now, why is it this way? Take it up with Steve Jobs. I mean, not Steve Jobs, Bill Gates, and maybe also Steve Allen. That's what I meant to say. Yeah, right. Because this is Microsoft's implementation of BASIC, right? So they're the ones who decided to do it this way. Blame them. Okay, now we haven't finished, right? There's still a couple of characters we haven't figured out what the heck is going on with them, right? And like what? Well, let's go up to the very top. Okay, and let me delete that. What's right here? That is print, but it's a single character. Is it the letter P? No, we wouldn't want to encode that. If we did, we would want to encode it as a letter. Okay, so what happens is all of the key words in BASIC get converted into what's called a token. Okay, and a token is a single byte, as opposed to how many bytes would we need to write the word print? Well, 5, right? It's just 1. These tokens have a special value, okay, and there's a list of them. I'll pull it up in a second. And that also actually answers, well, what's the only other thing missing that we haven't deduced? What do you think this one is? That's the go-to token, okay? Now, why is it maybe a good thing to tokenize, if you will, these files? It takes up less space in memory. That's essentially it, okay? The other thing is that it makes it easier for the interpreter, because if you hit the token for go-to, that's easier to know, like, oh, yeah, I'm about to do a go-to, rather than what happens if you hit the letter G? Well, you don't know. What happens if you hit the letter G-O? Well, you still don't know, right? So the code would be way more complicated on the interpreter side. Whereas if you can just look for a single value, that's easy, okay? Okay, so what we've got here are the tokens for go-to and for print, okay? All right, so let me put the Petsky, or not the Petsky table, but I want to put the basic tokens here, the list of the tokens. Okay, so here's the whole list. Okay, this is the list, by the way, for BASIC 2.0, which is the one that's on the Commodores. Other BASICs might have had different tokenization schemes or had more commands than what is available for us there. Okay, so for example, you'll notice that there's, like, literally those are all the basic commands that we have, period. You notice that there's nothing for drawing lines, for example, or draw a circle at this position on screen or something like that. It's possible to do those things, but you can't do them with a single command, okay? All right, so looking at this, does our stuff match the tokens that we found? Okay, what did we have? We had print. Was that 99? Did that match? Yes. Okay, and what was the other one? Go to, which was, yeah, 89 hex. That matched. Okay, and then of course there's a bunch of other ones here. Okay, does that kind of make sense? Okay, so what this means is if you write a program in BASIC not on the Commodore, like you open up a text editor or VS Code or whatever, and you type it out, how is it going to be putting, for example, print, if you type this in VS Code? Or any other text editor on a modern computer. So if you open up VS Code, 10, print, hello world, how is print going to get stored in that file? as the word print. It's just text, right? VS Code doesn't know it's basic, or your text editor has no clue it's basic. So could I take that text file and shove it onto the Commodore and run the program? Why not? Because it's stored differently, right? So what this means is if I want to take code that I write off of the Commodore and put it onto the Commodore, I need to tokenize it first, okay? Similarly, if I want to take code from the Commodore and read it in a text editor, I need to de-tokenize it so that print is actually the word print instead of some weird symbol. Okay, does that make sense, the issue here? Yeah? Okay, so I need to be able to tokenize and de-tokenize, and do you want to do it the way we just did it with this Excel spreadsheet? Hell no, right? Because wasn't that tedious? It took us how long to get that? 45 minutes, right, to get to this point? Ugh. Okay, and it's worse than that, right? Because it's not just converting print into the special thing, but also we got to get these pointers and line numbers and stuff properly encoded, right? So this is going to be a right pain in the butt to do, unless we have somebody else who's already done the work for us, or the evil professor makes you do it. Yeah. Ask anybody who took the class last year about basic tokenizers, okay, and they might start crying, okay, yeah. So how would we do this in an automated way? Because clearly doing this by hand is not practical. Okay, we can save it to a disk, right, but it's going to be saved in tokenized form if we save it on the Commodore, okay? So we want to be able to move files back and forth between a D64 file and our local files operating system. Okay, does that make sense? All right, so that's basically the problem. So there's two programs that we're going to use to handle this. Okay, so first thing let me do is let me save this and let me put it in our GitHub repository. And I'll upload that later. All right, so let me close that and let me also minimize this. Okay, I'm going to attach an empty disk image, and then I'm going to put this in the GitHub directory, if I can find it. And then my program okay. So then I'm going to detach the disk image from drive 8. Okay, that's like I just pulled the disk out of the computer. You need to do that for the next step. All right, so let me minimize Vice. Okay, and then let's see, downloads. Oops. And I want to go to O dash. Excuse me. Okay, so I've got a program on here called Droid, and oops. Okay, and so I'm going to run, in my case, it's a shell script. In y'all's case, it'll be or for Unix systems, so Mac included, that'll be a shell script. It'll be a batch file for those of you on Windows, and you have to run it from a terminal, okay, or PowerShell. So you can't just double click on it in your file browser to run it. You've got to be in a terminal, okay? Hmm? Yeah. Oh, you did? Oh, well then ask Michael how to get it to double click. right? I'm going to pull a reverse McCartan-Limb, and any PC questions go to Michael instead of any Mac questions come to me. Okay, so that will open up a window that looks like this. Okay. Well, you guys remember how, like, anytime there was a Mac question, he'd send you guys directly to me. Yeah, you didn't get to pass go, you didn't get to collect $200, right? So anyway, okay, so I have here, right, this is what Droid does. And what you see are two file system windows, and then there's a bunch of buttons. And what I'm going to do is on the either side, it doesn't matter. I'll do it on the left-hand side. I'm going to attach, I'm going to load my disk, and I'm going to load the same file that I did. So this is the D64 file that I had generated a moment ago on my emulator. Okay, and now what I'm looking at is the contents of it. Okay, so for example, if I want to copy this thing to my desktop, I can just, or actually, let's be smart about this and put it in, say, the GitHub repo. Okay, so I can take this file, okay, and I can copy file, and now it's over here on this side, and in fact, it helpfully appended .prg for me. Okay, I can do a couple of other things with this, and in fact, let me, on Mac, I discovered a new terminal called Warp, and oh my God, it is like the nicest looking thing ever. Once it loads, it sometimes takes a second for that part. Okay, but while it's loading, let me take my program and I'm going to hit here View Hex. And it's going to come up with a window. And let me, well, I should probably blow up the text, but can you guys read that at least okay for right this instant? What do we see? 0108 160A 0800 9922 48 blah, 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 blah. Does that look familiar? Yeah, it looks familiar. But there's one thing extra that we didn't have before. What is it? Okay, so if I put this next to our spreadsheet, there's two extra bytes here that we didn't, two extra entries that we didn't have in our spreadsheet. Where are they? Nope. At the very beginning, what are the very first two bytes? 0108. Okay. Why is that in the file, but it wasn't in memory? And what is so special about 0108 anyway? That's the pointer to where you're going to put this thing in memory. Okay, so the first two bytes of an executable file on a Commodore are always where is it going to get loaded into memory. Okay, for basic files, it's always 0108. Basic files always start at that memory address, period. But do we need to store the 0108 in memory? Like when we load the program into RAM, do we need that 0108 in memory? No, but we do need it when it's on the disk. Okay, right. So everything else corresponds exactly to what we had before. Okay, is that okay? Yeah. All right. So if I look at this program in hex, like essentially the file, what I'm seeing is what's on my actual floppy disk, all 33 bytes worth. Okay, how much of this is actually the program? Only 31 bytes worth, because there's that 2-byte little preamble, if you will, at the beginning. Okay, and if I look at this in ASCII, what do I see? There's a bunch of garbage, because none of those tokens are valid ASCII. Okay, all right, good. So the question is, how do we go in the reverse direction, right? So here, if I hit View Basic, okay, it will allow me to see, it will basically detokenize it so I can read it as plain text. And then I could save that file, for example, as a text file or print it or whatever, okay? If I hit C64 mode, it just kind of changes the font a little bit, but that's whatever. Okay, so if I wanted to save, that file, then I could save it here, and I could save it as hello, and then the extension that we typically use for basic is .base. And then let me reload the directory structure. Did I not put it in the right spot? Oh, okay. Well, it would help if your professor wasn't incompetent. Hmm? The token is saved as a single byte, right? And that's within, so I just didn't save this. Save, close, reload. There it is. Okay. So now I've got my hello basic text file. Okay. Now, if I look at it in hex, I'm going to see some extra stuff here. Okay. And because what is a basic file is just plain, like my source code is plain text, right? So how is print stored there? In detokenized form actually is the word print. Okay, so this is the file that I would open up in VS Code to edit or whatever. Okay, so this program will allow us to take something that's written on the Commodore and convert it into plain text that we could read, and also copy files back and forth. What about the other direction? How could I take this file and turn it back into a program? So essentially, I want to detokenize it. Not that one, sorry. Okay. Oh, that's right. Okay, so let's see. I don't think you can go the other direction with it, which is mildly annoying. Okay, but there is a second program that we can use. All right, so let me pop open Canvas for just one moment. Okay, and on Canvas, once it freaking loads, okay, while it's loading, I'm gonna pull something up over here off screen. Okay. Okay, so on Canvas, I've posted copies of Droid and C64 list. That's the other program I'm about to show you. They're in the files section under software, and then I've got Droid and C64 list. So C64 list is the one I'm about to use. Okay, and there's a user's guide there that will, of course, promptly not read because men never read manuals. All right, so in my terminal here, and let me blow up the font so that you guys can see this a little better. Okay. All right, so here's the problem that us Mac users have. You Windows users won't have it. Okay, you'll want to run this thing through a terminal or PowerShell because it's a terminal-only program. There's no GUI. Is anybody else? Well, Evan. Who else has a Mac? 1, 2, 3, 4. Just 4 of us. Okay. So how do we run this? Because it's .exe. That means it's a Windows executable. No, we don't have Windows on here, do we? Okay, so this is where we use this wine package that those of you who are using Windows don't need to worry about because you already are on Windows. Okay, now I've already installed wine on my system, but you guys will have to do it separately, and if you have issues, we can talk. Okay, so I'm going to do wine64 C64 list .exe, okay? Now, what I need to do is I need to give it a file, and you'll notice that this is one reason I absolutely love Warp. Sorry, PC users, it's not on Windows yet. Okay, so it's Mac only at the moment. They're working on it though. But you notice it's maybe a little hard to see in the projector, but you notice in gray how it's remembering past instances of when I used this command. Okay, and so the last time I used it was to convert oldwabash.bas to a program file called oldwabash.prog. That's to tokenize it. Okay, so if I have basic and I want to tokenize it, I'm going to use this. Okay, all right, so let me give it the file that I just created, which was that hello.base, okay, or basic. So that was located at GitHub CSC371 tokens hello.base. I'm program filing it, and then it's going to what was it? I want to call it the same directory, GitHub, or sorry, GitHub CSC371 tokens, and then I'm going to do hello2.prog. Okay. Huh? I will just hope that that doesn't work. Oh. Okay, hang on one second. Let me authorize that thing to actually run. So I've got to go to C security. And let's see, where's security? Allow anyway. It's because I haven't run that actual executable before, and so it's freaking out because, all right, so let's do it again. Okay, so of course that means that I'm typing something wrong. Well, you know what, guys? Let's read the manual, shall we? I know, right? It's well, the wine part of it is. So, okay, where did I put this? I think I put this in my downloads directory. Droid64 list. Okay. Yeah, so on Windows, you don't have to do wine64, then the name of the executable. You just have to do the name of the executable. Okay, so I probably am just mistyping something, so hang on one second. Oh, yes, it would help if I'm not an idiot. Okay, let me do this. Oop, dang it, I meant to do a colon there. This is a new version than I used last, so they may have changed something. Okay, so let me do this. Let me actually go to that GitHub directory, and I'm going to rename the. I'm going to rename. So I don't want to overwrite the thing that we already created, the hello dot the hello.prg. So let me rename it as hello-old. And then I should just be able to do this. Okay, that worked. Okay, so if I go to my GitHub directory, CSC371 and tokens, then what I'm going to see is, amongst other things, hello.prog. Okay, so this is what that program just created for me from my basic file. Okay, and if we look at it, so there's two things I can do. Let me actually rename it to hello2.prog. Okay, and the reason I wanted to do that is because then if I reload here, you'll notice I've got hello2.prog, right? And if I view the hex, I see all the same stuff that I would before. Okay, and now let me put this program file on this floppy drive. So I can copy it, and now hello2 is also on my floppy drive. Okay, which means I can go back in device, if it will come back up. Where did it go? All right, fine, we'll just quit you and restart you. If you want to be like that, we'll be like that. Don't make me force quit you. Okay, it's going to be that way. Okay, so now on the Commodore, if I attach disk to drive 8 and I load, let's see, we want to go to home, GitHub, CSC tokens, and this D64 file. And then if I load my directory structure, then I can see that my other program, the new version, is there. That's exactly the same program as what we had when we started, but what this means is we can actually write code else off the Commodore and then transfer it over. So I'd load it by saying load hello2 from drive 8, and there it is. And of course, it's messed up one of the characters, which I'm not sure why. Okay. Yeah, it's probably that weird space thing from my machine. I doubt you guys will have this problem. Okay. Anyway. Okay, so does that make sense? So what did we learn today? Two things, two big things. One, how can we move files back and forth from a real machine to a Commodore and vice versa? Okay, and then second, how are the basic files actually stored on both on disk and in memory on the Commodore? It's not in plain text. It's almost in plain text with some extra pointers and these tokens. Okay, and so what would be a great homework assignment for the professor to give you? How about write a tokenizer? It would be a really bad one. It's a really hard one. Okay. So hard, in fact, that only 3 people out of the 9 last year were able to actually do it. Okay. So good luck, everybody else. You know. Yeah. Anyway, no, it's complicated. because you've got to compute the pointers, you've got to compute the tokens. How do you know that you need to change print into a token? Because what happens if I had put the word print inside quotes? You wouldn't tokenize that, would you? But you would tokenize it if it appears outside of quotes. Yeah? Okay, anyway. All right, so I guess we can quit a smidge early. So I'll see you guys on Tuesday.